Okay.
Okay, you're live.
Okay. Welcome to Sustainable Thrust, an inquiry into ionic thrusters. I am Owen Gaffner.
And I am Ethan Vianney. What got us interested in ionic thrusters was, well, initially I was just scrolling through YouTube and I saw some future technologies, and one of them was ionic thrusters, and it got me interested in what it is. And honestly, I never thought that I'd be able to build one myself, but through the opportunity in this class, I was able to, and this was the result. So I guess we need to...
Okay, so a little bit of background. First, what an ionic thruster is. So I'm going to rely a little bit on the slide because there's a lot of words here. An electric propulsion system that generates thrust by ionizing a propellant gas and accelerating the ions using an electric field. So it's a more sustainable method of thrust compared to its fossil fuel using counterparts, and it is often employed in space travel. In fact, that seems to be the prevailing employment of the technology. So this was our design inspiration. When we decided to do the project, we figured we'd have to have at least a starting kind of blueprint to model our design after. We looked through a few different YouTubers' designs, and we found Integza. He does all sorts of scientific videos building many different machines. He has a couple that kind of went into the ionic thruster realm, and this was one of them. So we tried to emulate this design. At the bottom is that black portion, that's the transformer, which is getting some voltage from a DC power supply. You can see that red wire running up to the anode. That is a nickel piece that has been kind of cut into a crown shape. It will obviously get the charge from the transformer, and then it'll send that charge over to that cathode. That's a 3D printed piece that was then painted with conductive graphite spray and then electroplated with copper. So the anode takes that charge and it ionizes the air molecules, and then it forces or accelerates those air molecules through the cathode, creating some air velocity coming out the back of it, producing that thrust. Here's the bomb. We needed that nickel sheet to match what he had for the anode. We needed the copper plating kit and the 3D filament to 3D print our own cathode, and then also to electroplate it so it would be conductive. We needed a high voltage generator, which that is actually standing in place of our transformer. We needed that to up the voltage. We also needed conductive carbon paint. That was to make our 3D printed part conductive, to coat it with that copper. And then we also needed an anemometer to measure the air velocity coming out of the thruster. Okay, so the initial plan was to test a few different variables. The original ones we wanted to test were diameters. We ended up kind of moving away from that as we went on. We might get into that a little later. But we also wanted to touch on what the voltage input does. How does the air velocity change depending on how much voltage is being put in? What kind of relationship is it? Is it linear? Is it exponential? What we were going to measure, like I said, air velocity. That was going to be our metric going forward to determine kind of what relationships there were, what was taking place inside the thruster. But we had conflicts. I think it took about 15 prints to finally get what we needed. Here's just a couple examples of failures that I have no idea what the issue was. I never changed my file once. I just plugged it back in and eventually it worked. So like I said, those are just a couple of the issues we ran into. On the left, that actually messed up the printer quite a bit. A few of the components fell off of the printer and those needed to be fixed afterwards.
Yeah, and just a quick add, I did meet with my father. He's a designer, and he sometimes 3D prints stuff. So I changed the design, and I tried to print it out, and then the exact same issues were happening. So it made us question what in the world was going on. We kind of nailed it down to it was probably the filament in the printers, because the printers got used a lot in the Learning Commons. So we were able to use the printers over here
in the IME 100.
Yeah.
Yep.
And we ended up getting a lot better results.
Yes. Okay, so we also ran into some other conflicts. You can probably talk about those. You're more familiar with these.
Yeah, so with the transformers, we were able to buy the 3 to 6 volts transformers, and they boosted up to 400,000 kilovolts, or no, sorry, 400,000 volts or 400 kilovolts. And one of the main issues with them is they don't run for a very long time. So if you're trying to test multiple tests at one time, more than likely the transformer will blow up on you. Another issue was just the limitations in the voltage. So we couldn't go, I ended up buying 6 to 12 volt transformers to see more results, but past 12 volts we still couldn't
get any results.
Yeah, so that was some limitations on the input.
Yeah, you can go ahead and talk about
Yeah. So this is a couple of pictures of the assembled thruster. At the bottom you might notice the ruler. I was doing some optimization with our design to see what distance worked the best with our inputs. And you can also see there's a copper wire on the left-hand side, and then there's a crown on the right-hand side. The copper wire was just to see how the thruster would react with just having one point instead of having multiple points. Unfortunately, it didn't respond as well, so we went with the crown. But yeah, so this was the...
So you can see, it obviously looks a lot different, but it's got all the same components as in Texas, that inspiration we drew from. We have the transformer running up to our anode. Again, we used the crown design. Like you said, we stuck with what we originally were going to use from that example. And then we have a completely different shape kind of funnel there, the cathode, just because we designed our own, and when you're designing your own pieces, you kind of make things a little different. We raised it up a little bit. I'm not sure we had a particular reason for that, but we definitely went with a larger inlet diameter than he did. And then we also did a larger outlet diameter, just to maybe try to see if we can maximize the effects, get some larger forces out of the pressure coming out of there. Maybe we could reach a further distance or push over heavier objects.
Yep. So I was in charge of the design more, and the reason why it is raised up so high is because when we were initially thinking about what we wanted to test for, I had up to a 6-inch diameter funnel, and so it needed to be up in the air. If I wanted all of the tests to have the same starting point, I would need it to be raised up. So that's why it looks like that. Unfortunately, the bigger sizes were unsuccessful, so we were only able to get the 2-inch and 3-inch printed out and electroplated.
Yeah, go ahead and talk about how you kind of set it up, how you got your, what you tested, how you got your data.
Yep. So with the testing of this, I took everything home. I had to meet with Dr. Berry to get the power tester, because originally we were going to test everything in the Learning Commons, and their voltage generator only went up to 1 amp. So we needed more than 1 amp current. So that's why I needed to meet with Dr. Berry. Upon sending it up, I then tested from 3 volts all the way up to 12 volts and went by half-volt increment. And then I tested some different variables with the distance between the cathode and anode, and just kind of found the sweet spot for our data. And then the funnel exit diameter, I included all this inside of an Excel sheet that was then sent to Owen, and he was able to do hand calculations with it. So we had the input, or the large diameter and small diameter as variables, and then we had spacing.
We did have the smaller funnel that we did some testing with too. So even though we initially planned to focus more on change in diameters because of the printer issues, as well as maybe just some change in our mindset for what we wanted to accomplish, we did end up only testing 2, and we heavily focused, I believe, more on the 2-inch than on the 3-inch inlet diameter.
That is correct. And we focused a lot more heavily on how the change in voltage affected the output velocity. And then this
picture of it running. Yeah.
This was a picture. You can kind of see the plasma that gets produced.
It's hard to see with how dark the picture is, but to really be able to get a good view of the plasma, the lights did have to be out. You really couldn't see it when the lights were on. Demonstration. So we did want to run a demonstration. We planned on bringing a candle. I forgot the candle.
It's all good, though.
So we're just going to have it blow this piece of paper off the table.
And so the input voltage is going to be set at 7 volts. And
Impressive.
yeah.
Yes. Hold it.
Yeah.
Wow. Wow. Excellent. Okay.
That was the point in the project where things really started to turn around, up to the point of actually putting together the ionic thruster. We were getting discouraged. It seemed like everything was working against us. And then as soon as we got it to work, we both just essentially leapt for joy. We're like, we made it. We made an ionic thruster. And then we just kind of got a second wind to push forward on the project. It seemed like things were actually going to work smoothly from there. So yeah, we were able to move on.
Very good.
Here are the initial findings. So then, like he said, we tested with 2 different transformers, which kind of ends up with us having a little bit of a hiccup. We tested both of them at that 6 volt mark, but because we had 2 different transformers, they got 2 very different results. So when we went to go ahead and plotted different values, you'll see a weird like spot in the graph where it kind of transfers. But yeah, we did the test as high as we could with the first transformer. Then we switched to the second, try to give us a wider range of data. Paid attention to the amps on the test, and knowing the amps and the volts, we were able to use Ohm's law to calculate the power in watts. And we wanted that so that we could compare the power going in with the power coming out at the end to determine the efficiency. And then obviously we had the exit velocity measured using an anemometer. And we were able to, go ahead.
Yeah, I was going to say, as you can see, it only goes up to 9.5 volts. I wasn't able to get all the way to 12 volts because the transformers just kept burning up on me. So I had to, eventually I figured out that I had to only test one at a time and let the transformer sit for 30 minutes to cool down, and then test again, sit for 30 minutes. So it took a very long time to get the results in, but yeah.
And that again is with the 2-inch funnel. He did some testing with a 3-inch. We didn't end up getting too much data. We kind of just favored the 2-inch, sticking to the variable we decided to focus on, which was how did the voltage impact the exit velocity, as well as we'd end up checking a few other measurements we're going to talk about here, or calculations here next. Is that, okay.
Okay.
So with that data that we had, we decided to make a scatter plot with the voltage and the exit velocity that came out as a response. And then with that, we made a line of best fit that we could then plug into equations going forward. Okay. So you can see I had an R-squared value of 0.947. Looking at the chart, it doesn't look that great, but actually I feel like that's a pretty good value to be working with. It's obviously just estimates going forward using this. But we want to have a function of exit velocity according to voltage to then plug into a couple different formulas that we'll be getting to here momentarily. The first one of those was inlet velocity. We were curious what the velocity would be right at the entrance of the funnel. We knew that outside of the funnel, the air would be coming from 0. It was just resting in the atmosphere. But we wanted to know, since we knew how fast it was traveling as it came out, we wanted to know right at the entrance what the speed was. So we decided to set up a little graph there. I meant to, where that red squiggly is, that's supposed to have the equation for exit velocity. I think I missed that. But understanding that we only had one inlet and one exit, but we also had a change in diameters, decided to use mass conservation, and then also divided out density, since we knew the density would be the same at starting and ending. So what we had was A1, V1. So essentially had Q1 equal to Q2. So I divided the area of the inlet over to the other side so that we could solve for the inlet velocity in terms of that exit velocity. And we had that formula. So the line of best fit ended up being negative 12.8 plus 3.84 times the voltage. So we plugged that in, and that gives us a formula, and that numerically down there is negative 5.76 plus 1.728 volts. And that's in, times the volts. And that ends up giving us our velocity at the inlet in meters per second. So that was something we were just curious about, but then some of the other formulas were to give us actual informative information about what was taking place in the thruster that would help us kind of determine the plausibility of using this, where it may be applied. And so the next one was the thrust. We were curious what kind of thrust this put out, being that it is a thruster. So I took a formula for thrust from what I found online to be used for a fan. I figured this was working similarly to a fan. It was taking still air and it was pushing it through a confined area to accelerate the air. So I took thrust equals mass flow rate times change in velocity. And we know that the mass flow rate is density times area times the velocity. We had the density of air, we had the area because we knew the diameter, so we could calculate for area. And we knew that the exit velocity in this case was a function of voltage. We knew we had a relationship between the voltage that goes in and the velocity that comes out. So I decided to input that, and we also needed to note that the initial velocity, not talking about at the inlet, but talking about outside, the initial velocity was 0. So going forward, we have T, thrust, is a function of the exit velocity. So now we still have the density, area, exit velocity squared. Oh, the reason that's squared is because, yep, m dot v, and m dot in itself has the velocity in it, so we had the two velocities multiplying by each other. So now we wanted to look at the relationship between, so now we pulled in that equation we had for the exit velocity in terms of voltage from the line of best fit. We noted that, and then we plugged that into the thrust equation. So we ended up with the variables there, but numerically over there we had thrust is a function of voltage. Numerically it's 5 times 10 to the negative 4th times negative 12.8, there's our velocity function, plus 3.84 times v, and that gets squared, and that gives us thrust in terms of newtons.
And the units all work out?
We'll double check for the report. The last thing we want to take a look at was the thruster efficiency. We knew that I used a fan efficiency is equal to the power out divided by the power in. We knew the power in because we used Ohm's law, as we discussed earlier, having the voltage, having the current to multiply to give us the wattage. And then we just needed to calculate the power out. I found the formula for the power output of a fan is 1/2 mass flow rate times exit velocity squared. So we reworked that since we knew that exit velocity, again, is a function of the voltage. We input that voltage to calculate velocity again into the equation. And then that simplified over there to give us P out of the 2.52 times 10 to the negative 4th times our function, and that was cubed, and that gave us power out in watts. And then we took the power out and we were able to plug it into our efficiency equation and then decided to multiply it by 100 to get it in percent form. And when we did put that in, these different calculations go ahead. We are able to add onto our table and add in inlet velocity using these calculations for each data point, thrust, power output, and the efficiency. And what we saw really honestly surprised us. What we saw, especially on the efficiency side of things, it was extremely low. So that's 0.02% at the top, and then we only got as high as 10.6% at the bottom at 9.5 volts. So what first surprised us was how low of efficiency it was, and then the second surprise was how much the efficiency increased with voltage increase. So we found that an interesting relationship, and what we kind of talked about earlier today was, well, if this was running on a very high voltage system, maybe this would be a little more worthwhile because we'd end up with a higher efficiency if that trend is really the truth there. So
yeah, we didn't necessarily find our limitations on our design. We just went to what the transformer's limitations were.
And so for
Yes.
Yep. So just from that data, we were able to plot graphs of all the different variables we calculated in terms of the voltage. And what you'll find actually across the next, I think 2 more graphs after this, is if you watch the shape of that curve, it's almost identical on all the graphs. So you can go ahead and look. That was inlet velocity versus the voltage. Here's thrust versus the voltage, almost identical shape. Go ahead to efficiency versus voltage. If you hit the space bar, does it go to the next one? It should.
I don't know, maybe.
And then there's the efficiency. Starts out lower, but then again, it follows a very similar shape going on up to that 10.6%. So we wondered, like we said, we were surprised by the low efficiency. So we started to research why. And what we found was that ionic thrusters, because they put out such a low thrust compared to the more traditional methods, which would be like chemical, I forget the word, chemical and, or sorry, well, jet engines and things of the sort and whatnot. Yep. So such a low thrust compared to those, it's also made with the use in mind of being in space, in a vacuum. It's functioning in a completely different environment, and they require a significant amount of electrical power to ionize the air and then accelerate the ions. So why is it different in space than it is here on Earth? It's simple. We have the atmosphere. The atmospheric pressure and the density interfere with the ionization and the acceleration of the ions. The atmosphere is actively working against the process of the ionic thruster.
Also, something to note, in space, I believe they use xenon
Yes, they do.
as a gas, and this just uses
The air.
oxygen or the air.
So, to kind of conclude, we had many hiccups throughout, especially early on, but we kind of powered through with help, thanks to you, Dr. Perry, and you kind of encouraged us when we were considering stopping. We were able to construct, one of our main goals was to construct an ionic thruster, and that we achieved, and that made us very happy and helped us to kind of keep going. We identified the relationship between the voltage and the exit velocity, and we were able to use that relationship to uncover others, to see how,
So how
yes.
about that, a parametric expression, a parametric relationship?
Yep. Yep, and we were able to figure out those parametric relationships between the voltage and these other variables like the power coming out, the thrust, the efficiency. And we found that though ionic thrusters offer a more sustainable means of producing thrust than more common fossil fuel devices, such as we talked about jet engines and whatnot, we did determine them to not be a practical alternative to just replace them, at least not in the atmosphere.
Not in the atmosphere,
Yeah.
but in space.
In space, most certainly.
Right.
Most certainly, because it doesn't have the atmosphere to contend with. So unless something changes, unless the technology changes or something's developed, we didn't see it as a reasonable replacement for things such as jet engines. And then also we had kind of some parting thoughts after that. We definitely learned a lot. We tried new things. We were able to work with new equipment, new tools. I hadn't worked with 3D printers in several years. It was kind of, at first it was fun to get back into it, but then we saw all the issues and how kind of tricky they can be. We depended on others for help several times. We depended on you, Dr. Barry. We were able to depend on Professor Watchhorn and some other people to get us access to, Kurt, and Kurt got us the different tools we needed. We gained an appreciation for ionic thrusters. We had a hard time getting this to work, and it made us appreciate it that much more when it did work. And we also gained appreciation for scientific experimentation, just seeing, thinking about the patience it takes to have an idea that you don't know if it's going to work, and then to put in the time, the labor to try to bring it about, and to face some setbacks along the way, but to still maintain that resolve to keep going and uncover something new or something that at least you didn't know. We also made some good memories, and we got out of a final exam. So we would 10 out of 10 recommend the project option to any future students. We thought it was a great learning experience. We've sat through dozens and dozens of final exams here at Kettering. I can't say that they really offered me a beneficial experience that helped me along, but I could see this project leaving some thoughts and memories that'll last a while and kind of help spark some interest in some different areas. Any final parting thoughts?
Yeah, I just really appreciate the opportunity that was given to be able to make something that I saw online that I never thought that I'd actually be able to make. So it was a really cool experience, and I definitely recommend people to chase after whatever they're interested in, no matter how impossible it may seem.
Fantastic. Great job. I have a couple parting thoughts as
Okay.
well. Let me just go next door